6-story passive house mixed-use building with retail and restaurant use on the first story and 52 rental dwelling units on the upper stories under the secure market rental policy. The site is located at the intersection between Rupert Street and East 22nd Avenue. This is the current construction progress so far.
So you can see we're framing the level 5, and we're also, you can see on the concrete floor, we're already installing the storefront, which is vinyl windows, which we're going to talk about later.
Right. So we will be focusing on the 5 themes, and both the design team and the construction team will have different issues to consider. So starting from the compactness, the peak's surface area to volume ratio doesn't look too bad. It's within the favorable compactness ratio, and it's similar to 2 of our other passive house projects, the Heights and the Little Mountain co-housing. So however, the building massing is still stepped quite a bit. This is primarily driven by the planning department's urban design agenda and the client's desire to maximize unit count and FSR. So the complicated site condition and sloping also adds complexity to the building form.
So this is a 3D representation that the structural consultant sent us. It was really interesting because it shows how the consultants are really involved in the project for this one.
So the form factor of the building is important as it directly affects how much insulation is required. The graph shows a heat loss form factor. So as the ratio gets lower, the required average building U value can be higher, which means the walls and window can have less insulation. So from a modeling standpoint, fewer corners means fewer thermal bridges to model. And this was our list of thermal bridge inputs in our PHPP model. And also simplifying window types and reducing the number of mullions will help a lot as well. So what we found was that solar heat gain should not be relied on as a major contributor to heat gain. What we want to do is to balance the solar heat gains and shading, so the heating demand is as close to 15 kilowatt as possible. And if the heating demand is too low, it means the building is likely to overheat too high and you don't achieve passive house. So the high our windows are high performance Innotech windows and doors, and they are certified PHI component.
I see George is on
Those
the
are the
call from
windows.
Unitech.
Yeah.
Sorry. Jeremy, go.
So the windows are, sorry. So we're using those windows for the storefront and the units, and those are really heavy, so it's hard to install, and we decided to go with a professional installer, so Innotech is installing them too, instead of what we usually do, which is the framers. And also the cost on those windows is slightly higher due to the performance.
And so the other thing is there are multiple methods to limit overheating. So the passive method would be opening windows and using fixed shading or deep balconies. The active method would be operable shades and with supply air cooling using heat pumps. There are also rough-ins for ceiling fans. Smart glass or self-tinting glass can be considered if required. So regarding shading, we originally decided to go with manual sliding shades since it's mechanically simpler and it's a passive system. However, as we discovered, the mounting details are more difficult to deal with from a building envelope standpoint, and also the amount shaded can vary greatly as it depends on the angle of the sun, and it relies on the occupant to manually move the shades.
Yeah,
And,
so we also had
oh,
issues with
oh,
supply
sorry.
because we didn't have many suppliers from local suppliers. All the suppliers we found were from Europe, and the cost was therefore higher. And with the COVID situation, we're a bit preoccupied of the delays that could generate.
Yeah, and when we also found that modeling these, we have to model the shades twice, and the weighted average is used. And these all increase the variable in the model, which affects the accuracy. So after a pricing exercise by Bold, we decided to go with the automated exterior blind from MHZ. So these provides a constant 92% shading throughout and allows for higher solar heat gain glass, and it's automated for better control. These are also solar power with rechargeable batteries.
Also in the install side, they are easier to install, and we avoid all the detail we had to do with the other shades. So there's no envelope issues with those.
So we had RDH do a critical suite and overheating analysis on the building. And the results were under the current model, there are only 5 hours above the 80% acceptability limit. But with the 2050s model, overheating becomes more of an issue at around 602 hours. These were modeled with the exterior manual shades and partial mechanical cooling. Another important design challenge is detailing the continuity of air barrier in section and in plan. And Bo can speak a bit about the education of the trades.
Yeah, this is the one we're working on right now because we're doing the framing, which is a key part for the air tightness. So we had a conference with E3 who helped us and the trades to prepare for the air tightness for all the pre-stripping on the walls and the ring joist. And that was really useful for everybody. It was nice to see that all the trades were really involved in keeping the building airtight.
So the air tightness is pretty critical in meeting the 0.6 air changes per hour for passive phones. So for visualization, that's 400 square inch of hole for the entire building envelope, or it's equivalent to 4 letter size pieces of paper. And here's a sequencing diagram of how the air barrier is installed at the floor lines. So basically the floppy piece of air barrier membrane is wrapped around the rim joist and is connected to the wall above. And here's just a construction image.
Yeah, so we have different details, some at the edge of the deck, some at the edge of the building, and transitions between outside parts and interior parts.
And smart membranes were used on this project to allow for more insulation the roof cavity. This is because it allows drying to the interior. Another consideration to control air leakage is with Epdm gaskets. Every penetration through the air barrier should have an Epdm gasket sealed to it.
So we haven't done that on site yet because we're doing the framing right now, but we've already discussed that with Cornerstone and the consultants. And that's an example from another project from Luke, I think.
So, and due to the complexity of the details, we've developed a 3D model to visualize all the components. So this shows the membrane pre-stripping and taping required at the different interfaces. This is showing the overhang and the rainwater leader. This is with the cladding and the curb. This is at the interior layers. So we found the mock-up was really helpful with both the design team and the construction team. This is the current mock-up on site.
Yeah, right now we're working on the decks there.
And here's just a window detail at the floor line. That's the current site condition. So our main exterior wall assembly achieved the R value of 31. There's the roof assembly, which shows the smart membrane in green at the underside of the joist, which allows the cavity to be filled with blow-in fiberglass insulation. So our roof has a step structure to fit the ventilation ducts and the DX coils in the ceiling of the space. So another design decision was to move the rainwater leader from inside of the building to the exterior of the building to reduce heat loss. And the challenge was to keep it away from the walls for waterproofing and as a way to, or come up with a way to slot it through the balcony. So our mechanical contractor, Omega, provided a solution to drop in a single continuous stainless steel pipe through the balconies. And at every level, there will be Menzies and storm collars for waterproofing.
And as a shop drawing they provided last week, so we're working on it right now with Luke.
And this is showing the deck transitions. This one is showing the concrete detail and the inverted roof design at the concrete level. This is a current progress photo at the slab edge. And this is a window curve detail at the concrete level. And this is the interior side where the wood furring are kept off the concrete with thermal clips to reduce thermal bridging. This is showing a window curve waterproofing at the concrete level. And this is the window install detail.
Yeah, so we have the window already installed and we're ready for the testing soon.
So, and another big heat loss element is the plumbing vents. So one way to resolve that is with the use of AAVs and papas. And currently there's an alternative solution to use these exterior rated AAVs only on the roof of the building. And that's been accepted by the city of Vancouver. The ideal way is to remove all the other venting or other branches. So blower door test for air tightness will be one of the key elements at the commissioning stage.
So we're not
One
yet,
of the things,
we're gonna
sorry.
go to the 6th floor to do kind of a mock-up for the whole building to kind of find the leaky points on that one unit.
Yeah, so what we've done is we've isolated one suite. We're going to be taping the floor, doing special preparation around it so that we have one good sample to test our exterior wall, our parapet, and our roof assemblies to see how we're doing.
Yeah, so yeah, all the ducts will have to be sealed. And for a full building test, holes will need to be left in the wall if there's no common corridor. But in our case, we do have a common corridor. So another important item is the Hrvs or ERVs. So one stack typically serves around 9 suites with 2 suites per floor. And there's one heat pump on the roof to temper the supply air with some cooling and heating. And it's controlled by the ERV. This is a typical floor showing the suites served by each ERV stack. The ERV are located on the roof with the DX coil in the ceiling below. And by zoning the suites into stacks, it allows for similar temperature condition per stack based on the sun's position to control the temperature of the air being supplied.
So one of the keys on that floor is we
Yeah.
wanted to put the cooling coil and heating coil within the thermal envelope. And so we've elected to kind of come through the roof out into the corridor where we can service that coil and then back down into this vertical stack of the suites for the supply side.
And also the system allows for different temperature set points. So for hot water generation, we're using the sand and CO2 heat pump because it's more cost effective compared to conventional water heaters. For this project, we're using 4 sand units linked in series to provide all the hot water required. And all the hot water pipes are measured to provide a more accurate model of the internal heat gains. And yeah, that's it.